Welcome everyone. Manasvita Joshi, and she's University. PhD from Ohio University in 2009, and physical acceleration scenario. And
hello everyone. People, and I'll be talking to more people after this. Last year on understanding the spectral energy distribution of blazars, or each orientation of the magnetic field of blazars. So the main to understand the phenomena near black holes and relativistic field and particle acceleration, variability in both their flux and polarization. A lot more in the optical than originating from smaller volumes. The knowledge of the structure of the field to the formation and propagation of the jet, and I'm sure Lawrence. So the fact that it is, but the structure of the emission from these sources by few people, but on helical geometry. So various geometries that could exist inside a relativistic jet. Investigate the effects of each of those geometries blazars. And for this study, we Joshi et al. 2014 to understand how the orientation. Some of the questions that we are trying to answer here is how for different orientations of the field. Of blazars in a given orientation, or synchrotron and SSC component change at all as you, and are there any intrinsic differences between spectrum radio quasars and the BLX which could arise. This is really a topic of a separate talk altogether, so So to carry out the study, we are using the multi-zone model of radiation transfer time-dependent leptonic jet model, which is based on internal shock model. So you have two feed with different mass content, and they collide with each other at a certain distance to form a single merged shell. And toward the emission region, they accelerate particles, and those particles then start radiating. Now, region. So the region geometry is cylindrical in nature, and it is sliced into multiple side. So this takes care of the radiative transfer that takes place from one zone to another, and the entire scheme is followed. Light travel time effect to correctly account for the origin of the photon from a given zone. This entire scheme is then put inside Compton component, and we consider all the accretion disk, the broad words producing the external Compton component is then modified to address that. Well, step one is just the magnetic field orientation, and using that you calculate the corresponding synchrotron. Considering we calculate our plasma frame or in the co-moving frame, and using that, and then we look at how to calculate this synchrotron emissivity. We have actually the Bessel function, which goes into the time. So anyone who's interested, I can talk about the to what happens when we start introducing. So in order to construct a base set correspond to that of to see what SED and light curve we get from considering the usual approach. The emission region, the starting point of the emission region is at 0.04 parsec, or around 10 to the 5 gravitational radii away from the central engine. And the strength of the magnetic field that has been considered is of an order of Gauss. The superluminal cone of the source is spread over an angle of 3.6 degrees. For this particular parameter set, our viewing angle that has been considered is of 124 stability time scale that we were considering to construct the base set. Time averaged SED. So as you can see, the optical range is as expected, guided by component. Range, it is really a combination of the external component due to the dusty torus and some portion of SSC. And by the time you move to the Fermi range, the 10 GeV range, it is really only coming from the BLR. So this and the components that I apologize for that, are the two radiative feedback components that I'm trying to show here, but they are actually in gray and it's not very visible. In any So using this as our base set, all we do, I'm only going to really talk about the first one is where in that case actually is only just a function of the Doppler factor. The says when we start to vary the viewing angle, you observe two interesting effects. One, the synchrotron component is guided or governed by the sign of the viewing angle, which means if the viewing angle becomes small, the synchrotron component goes down. On the other hand, the external Compton component continues to be guided by the Doppler beaming factor, which means if the viewing angle is small, you will still get a boost in the external Compton. So this kind of, in this case, for a smaller viewing angle of 0.1 degrees shown in red, what we see is A, the Compton dominance becomes hardness depending on the components which toward its radiation. So for example, now which is located around is now actually coming from the overall profile remains the same. So if you compare the profile of our tangled magnetic field at a viewing angle of 1.3 with a parallel orientation at the same angle of 1.3, the overall profile doesn't really change. So just by looking at the light curves, we would not be able to pinpoint or single out that whether it's due to a parallel geometry or not. So for that, we will actually have to look at the SED, look at its Compton dominance and its hardness to comment on the geometry of the magnetic field. On the other hand, for smaller viewing angle or larger viewing angle, the peaking happens sooner or later depending on the viewing angle, and that's basically because in the case of a smaller viewing angle, photons are now taking a shorter time to reach from the far side of the emission region to the near side. So that decides when the flare peaks when you change the viewing angle. Now, another signature means in terms of polarization, you should see a perpendicular polarization, a polarization that is oriented perpendicular to the jet axis. And along with that, you should also see a low degree of polarization because it would mean that there is fading in the synchrotron. And three of a scenario. So I'm just pointing out the two cases that we are considering right now. We have to sift through some of the data to really pinpoint when this kind of a behavior was observed. Because this type of Moving on to the oblique geometry, this is when to the z-axis. So in this, the z-axis and its projection. What happens is, when you look at the SED, as you change the obliquity of the magnetic field, you start to see how the Compton dominance and the spectral hardness of the SED is changing, with one particular scenario becoming quite interesting, which is when for the same viewing angle 1.3 degree, your magnetic field makes an angle of 45 degree with the z-axis and is located at a 0 degree angle in the xy plane. And what you see is, for the same viewing angle, you notice a dip in the synchrotron, whereas nothing happens to the external Compton. So this kind of a scenario could actually pinpoint to some of the orphan flares that are observed in blazars, where you don't see much happening or nothing happening at all in the synchrotron, but you still get a flare in the external Compton, or spectral hardness also changes as you change the obliquity of the magnetic field in the xy plane. So just to give you an example of this type of a behavior which was seen, similar behavior is, this is from the blazar PKS 1510 -089, and if you look at flare number 7, what had happened was you did see a flare in the gamma ray, but there was nothing in the optical, in the R band. And what I don't have the plot for that is, there was also a slight dip in the degree of polarization in the R band. So all these components do signal toward an oblique geometry of the magnetic field in the source, in this source. Then the next is purely toroidal magnetic field around the function of the azimuthal angle, which the either it starts this would be another type of a signature that can be used to see if a toroidal field exists in a particular blazar, depending on what is really happening in the MEV and the GeV range. Now, the light curve profile, so I'm just showing the R band here. As you can see, in case of the overall profile, they don't change except for their overall flux level. So the profile from the randomly oriented case shown in black to the one in green for the same viewing angle of 1.3 degree remains the same, but flux level obviously gets enhanced. And when you reduce your viewing angle to 0.1 degree or 2.1 degree, as I had mentioned later, the peaking of the flare profile gets affected. But other than that, there are no telltale signs as to that this really points to a toroidal geometry. And then this I have already covered. Finally, the helical geometry looks very similar to what we had seen in the toroidal case. So we what that data indicate. But as you can see, when you are moving it through your z-axis, because in this case your pitch angle is now also a function of the angle which the helix makes with the jet axis, with the z-axis. So when you change that helicity, there is an overall change in the SED. The change is not as pronounced because this change from 30 to 60 degree is in the co-moving frame. So for us in the observer's frame, it's only a change from 2 to 1 degree, or 1 to 2 degrees. So it's a very small change. So that's why it is not as pronounced. But the idea is that as you change the helicity, it is going to impact the overall flux level of your SED, but will not really change the Compton dominance or the spectral hardness from one helicity to the other. This is just a I didn't talk about because it was not an interesting case. It did not show any interesting features which we will be able to distinguish from a randomly oriented magnetic field. And that is understood because when you are considering a transverse magnetic field, you really don't see any variation make in the light curve. And then different, but a combination of the Compton dominance and the spectral hardness will be able to indicate what kind of geometry we. This is an ongoing work. Right now, we have not considered any kind of the magnetic field strength and to its original position. So this to what would really be seen in blazars to understand how the orientation of the magnetic field. So the work which is still remaining is to which through that we will be able to then address a larger class and the EVPA, and it could be low during an orphan flare, as was seen of 2009, for which I showed there. So these are some of that. I will be happy to take questions.
I apologize if the question is not well defined, but the suppression in which in some approach.
Either that with the jet axis, then that.
Looking at the different where the synchrotron and the line of signs being.
Yeah, so which was the parallel case that have the magnetic field. Oh, are you talking about the parallel? There is that special combination only.
Yes. The moving frame, you're still looking a lot around that.
Around that, yeah, that is correct. So in case which I did not touch upon here, the degree of polarization to reach as not a highly ordered is like 70 or 72%. Some contribution from the disordered component. So which is why if I reduce the disordered component and then, but this attempt was to really just focus when you just assume a purely ordered.
Please excuse me if this is AGN that caused the magnetic field. What kind of AGN produces? And is that an observation?
No, so that is so all these, including plasma effects, and see what can orient or they can stretch in orientation. But to be able to comment on so.
I know you did this for blazars, but could this also help or anything like that? Can we see it either?
Use internal shock model to get this model to address magnetic field can do there. So those.
From upstairs.
Thank you.
Our government, and he's visiting us all the way from Japan. Really good. And he actually started his astronomy research here when he was a pre-doc at the Center for Astrophysics. Later, he completed his PhD from University of Virginia. And he did his postdoc research at Potsdam Institute and Zurich. And currently, his research group is mostly studying the evolution of galaxies and the supermassive black holes.
So thank you very much. It's nice to be back. The room is definitely smaller than I remember. Hope I haven't gotten bigger. So yeah, I see a lot of young people. So I'd like to just mention that I work at Kali IPMU in Japan, and it's actually an international research organization that is has English as the official language, and half the people there are foreigners. And so people about that. So today I'm going to talk about starburst galaxies, so it's a little bit lower energy than what we heard about and maybe for the session, but I did throw a slide in of X-rays, so I'll try to keep people interested. In Asia, another good thing about Asia is that the better. To high redshift, so you see the star formation rate density that we're all familiar with, probably, as increasing up to redshift 2 and 3. And so we'd simply like to know, what's. It could just simply be the amount of fuel that you have, the amount of gas that's there in galaxies that's going into forming stars and also fueling the black hole. Time. And so these are some models based on observations that show that all galaxies, the whole population is ramping up in terms of the amount of gas as you go to high redshift. And so is it just simply the gas fraction? Well, I'm not going to talk about the overall general star-forming population, but out of those, select the starbursts, just as a first attempt to try to look at how stars are forming in galaxies where they're forming at the highest rates, okay, hundreds of solar masses per year, you'll see. Seeing the star-forming population. So at redshift 0, we have a star-forming population that's been studied to death, the ULERGs. And so we know something about their gas masses through carbon monoxide, as I'll mention. But it's a so you need to use efficiency. How efficient are these galaxies at forming stars? And then really what I want to do is talk about using ALMA to look at the high Z starbursts and seeing if they're any different from what we see in the local universe. because we are seeing dramatic changes in the galaxy population, as I'll show. That we've been working on for the last 4 years, because I'm going to select the starbursts out of this spectroscopic sample. Redshift to know how to tune your interferometer to know where to look for infrared spectroscopic survey with Subaru telescope. Today, if you want to do a galaxy survey, you really got to get over this barrier. And so after 4 years, we had 60 nights on Subaru telescope. Typical lines that you see in the optical, the ISM at high redshift, just like what you can do with Sloan. 400 fibers, and in one pointing, you can look at 200 galaxies. If you put about 5 hours, you can very well detect H alpha in the H band. All 4 lines to be able to do dust correction rates. The other lines tell you something about the metallicity, the chemical. The field of view in one pointing is 0.2 square degrees. So with 4, which are the starbursts at high redshift, because of the atmosphere. So what you see here is our sources, and in cyan here, in magenta, are all the OH lines of the spectral window. So we really have to look between these lines. Forest. Okay. But I would like to highlight one result that we recently, what we call the Baldwin-Phillips-Turlovich diagram of looking at to separate star-forming galaxies, which you see in a sequence here, state of the ISM. So if you want to do above this dividing line or star-forming galaxies below. Okay. O3 to H beta, and they're actually shifted to at stars that are ionizing the gas. And so what this does, and so what it means is when you go to high redshift, this whole thing is shifting up. The AGN is sitting there. AGN star-forming galaxies at higher redshift. But there's also, and I can show you that a little bit better with this illustration. This is now comparing the location in the BPT diagram of galaxies sitting here, where at high redshift, at redshift 1.6, you're being elevated in O3 to H beta. But you're essentially at the same metallicity. So these are galaxies that are fully enriched, but they're still forming stars. In mass, you get further offset in N2 to H alpha, so the metallicities change. Okay. And so one of the things that we have to be careful of, this is the AGN are ramping up. There's many more at high redshift than there are at low redshift. Seeing. And so what we did here, this is all in the cosmos. You can stack the X-ray data. And so these are bins of stellar mass. If you didn't have the X-ray coverage, you would just stack everything. And what you see here is a soft and hard. So there's always some underlying X-ray population when you just stack everything. We tried to get rid of all the individual detections as we could. And so we think that but the question is, if those massive galaxies have to be that the AGN might be doing something. We don't know yet. From from non-AGN, you can have low mass X-ray binary signal is, and we're trying to work on that. Okay, now to the starbursts. So it turns out it's going to be a little bit different in how you want to select a starburst galaxy at high redshift and low redshift. At low, starburst galaxies are very dusty. You want some signs of nearby neighbors. They're all, as we know, in major mergers. But here's the problem. So, well, at between star formation rate and stellar mass, which I'm going to use the term main sequence. It causes a lot of trouble because there's a main sequence for stars, but let's just call it main sequence of star-forming galaxies. So when you do this selection in a main sequence is rising for all masses, and so off the main sequence with things that are very massive galaxies, but still typical star-forming galaxies. They're still disks. Just the submillimeter samples just by this cut in star formation rate. And so what we're going to try to do is have a cleaner selection than that. So what we want to look at high redshift are things that, whether these starbursts at high redshift are similar or not to local ULIRGs. So local ULIRGs are known to have large amounts of molecular gas. So we'd like to check whether this is true at high redshift. These local ULIRGs are actually very interesting in that all the gas, all the star formation rate is nuclear. It's within a kiloparsec. So is this also true at high redshift? And they have an elevated star formation efficiency. And I'll show you what I mean in the next slide. So this is what people are probably familiar with, a Schmidt-Kennicott law, that given a gas surface density, there's going to be a corresponding star formation rate density. And so for typical star-forming galaxies at low redshift, there's going to be there's a tight relationship between have been found to be offset, that at a given star formation rate density, they have less CO, less gas, I should say, as the typical star-forming galaxies. So they're more efficient. They don't need as much gas to get their star formation. Are we seeing two different modes of disk galaxies and maybe a merger phase where things will jump off this relation, and you'll have two different modes here? Okay. Gas mass. Two of them, we're going to attempt to measure a dynamical mass by actually the gas. Okay. These are the main sequence galaxies that we've been looking at with FMOS. These are our parent target galaxies. And the Herschel sources are in red, anything that's detected in the far infrared. So we're now going to do a selection based on a cut parallel to the main sequence. with
sequence for that Z.
yes. So these are just UV-based star formation rates. Now these aren't actually the star formation rates that we measure from H alpha. Four of our targets, and this is where you can see the SED in the far infrared. So with Herschel, PAX, Inspire, you actually get the peak of the far infrared distribution, and it fits. Sorry. And here's a nice comparison of an SED of a very dusty galaxy compared to if there was no dust at all, which would peak in the UV. So these things are really that we're going to look at. And here I'm showing the FMOS spectra where you can see the H alpha here. Which is interesting, about 600 kilometers per second. Usually these lines are around 200 to 300 kilometers per second. As well, the ground-based infrared to get the stellar mass measurement. CO, we want to use a low order transition as possible, so we're going to use CO2 to galaxies. If you use higher order transitions, those are going to be probing denser molecular clouds. So starbursts. But what we're going to have to do is use this conversion factor of going from a luminosity in CO to a massive contention as to what these alpha CO values are, because it depends upon the things. We're getting consistent results. Get 2 to 1 in band 3. So CO 2 to 1 is at 230. They're about 90 gigahertz. And two sources came back with the other three were more about 5 arc seconds. So we only wanted to measure a total CO. Two of them came back at higher resolution. We actually did resolve them. And so here are the two. It was really nice that they came. And so plus for the ALMA, we're going to add 2 more sources from IRIM that were supplied by one of the COIs. The 7 sources. The images that I'm showing here are HST, the CO contours. So all of them are detected above 5 sigma. Is that these are very heavily obscured. So it turns out in the UV, in the rest frame UV, but falling somewhere in between here, and it's actually a peak of this infrared knot. I can blow up one of them. So here's one where there's multiple components. It's probably a major merger of these different knots coming in. Nice with the infrared component. And here's another one where we be right in between 2 peaks in the infrared map. So it looks like, and CO is probably indicative of the whole system here.
What's a physical?
Go back. So, and so we're this is about here. Let's see. This is about a kiloparsec across. Sorry, 10 kiloparsec. Here we're getting something that's very extended, and this whole thing is actually rotating, so there's actually rotation to the system as well. Any gas mass, we can just look at observables. So this is now total infrared luminosity versus the luminosity in CO. Fall along your Schmidt-Kennicott relation would fall along this relation. So the local ULERGs would then be a factor of 3 below this in terms of CO at a given infrared luminosity. And so this is the local. Not bright enough to put them in line with typical star-forming galaxies. Okay? And so they seem to fall between the two. And so there's about a 1. And doing the same for the specific star formation rate. And so if there's a change in the CO emission relative to star formation, here's your typical star-forming galaxies transitioning to the ULERGs. These are nicely filling in of what I'll say is an efficiency of converting gas to stars rather than just having a bimodal distribution. Since we had 1 arcsecond resolution, and so we can take the velocity of the line profile okay? And the reason why we want to do this is we can get a dynamical mass, and then we can and remove a dark matter component that we have to assume is a quarter of the dynamical mass. So this is just very rough. Just we get. And here we get an alpha CO, and we can compare this gas mass to the I don't even give an error because it's very hard to give an error. So this is just just to get a we definitely need a larger sample and understand any systematics in this. So I'm not trying to argue that this is really. To our CO luminosities, we get gas fractions of around 30 to 50%. Very similar to the gas fractions of typical normal star-forming galaxies at these redshifts. So then these starbursts are not off the main sequence because they have very high gas fractions relative to those galaxies in the main sequence. Okay, so it's year, these galaxies are down by about a factor of 6. So in about 50 million years, these galaxies would have depleted all their gas, gain about a factor of 10 to the 10 gain another 10 to the 10 in stellar. So we really think we're filling in this population. There might be some transition. Haven't had these samples where things that aren't so elevated off the main sequence by looking mostly at these, really extreme ULERGs at low redshift. There are results. There's also a paper by Nick Scoville who's using the continuum to do the same measurements, and there's some contention as to whether you couldn't have both factors at play. Okay? So I'll just end there that at high redshift, we definitely see lower CO given the total change in star formation efficiency, probably driven by galaxy mergers, because most of these galaxies often they have very high, they fall in a region of the BPT diagram that is in a composite region. As compared to typical star-forming galaxies. So what we're trying to do now, we actually have some more observations. We're trying to go further off the main sequence, a factor of 8 higher, to see whether we can really see this whole change. This guy is at redshift 1.5, it's at 2,000 solar masses per year. To the other ones. But it's really interesting, at 2,000 solar masses per year, it's got to be shut. Really a large gas reservoir. And so we need to go back and look at these at high resolution now, because this is about a 2 millijansky source. So once you can find these rare things,
Yeah, I have a question. When you determine alpha, you had to estimate the stellar mass. I assume you did that with some because they're infrared emitters because they block out most of the stellar light.
yeah.
So extinction must be your
from the infrared, from the Spitzer, so 24 micron, and going as redward as we can, where we're sensitive to stellar mass. So it's bigger-ish. So I think getting the mass from the infrared, not being too weighted by the UV because it's completely extincted, is one of the issues. But I think we're okay with that. We're able to get the proper stellar mass, the deblending to make sure we're actually getting the mass of that.
So you were mentioning that those star-forming galaxies and at higher redshift, you think they may be triggered by merger?
They're not in overdense regions, so I know that. What we really need is the go on is the UV emission, and whether we're seeing knots of UV emission or dusty lanes of. But most. It's a problem because that conversion factor depends strongly on metallicity, which has been well demonstrated, and so we have the metallicity from the
Any other questions? If not, let's thank all our speakers.
Do I have to shut this off?
should have nothing to do with metallicity. the reason